This tutorial will demonstrate how to construct the following network. The most important feature of this network is that it oscillates. So if you click on this simulate button and then simulate, you will notice that it oscillates. The reason for this oscillation is this negative feedback, which is further strengthened by this positive feedback. This particular network also stores the sequence information. For example, if you click on this sequence button, you will see the complete sequence of the strand of DNA starting from this O1 operator sites. So if I double click on this DNA sequence, it will show me the sequence, the part corresponding to that sequence. So not only is it storing the kinetic information, but also the sequence information in addition to other information. So let's construct this network by opening a new window. Then I'm going to insert a coding segment. Now if the coding segment is not in the recent items list, it will be here in this complete parts list. So I'm going to insert a coding segment and then a protein. I also need the intermediate mRNA. And then I am going to insert a transcription reaction from C1 to mRNA and mRNA to this protein. So a transcription reaction is this one, transcription. Now if I accidentally select the wrong type of reaction, TinkerCell will automatically correct and select the matching reaction. Now let's see what these reactions mean. So if I double click on this reaction arc and look at the rates, it says the rate is 0. The reason for that is because there is no promoter upstream of this coding segment. Now if I look at the rate here, it shows me that the rate is proportional to the mRNA. But this particular reaction also says it consumes mRNA, which is not true, so I'm going to put 0 there. Then I'm going to select the mRNA. First let me move all these. I'm going to select the mRNA and the protein and insert degradation reactions on both of them. Then I'm going to rename this to the LAC-I protein and then the LAC-I gene that's producing the LAC-I protein. Now I'm going to select this entire region and paste it, make a duplicate, and that will be my ERA C gene and the ERA C protein, capital ERA C. Now I'm going to insert ribosomal binding sites upstream of each of these coding segments. So ribosome binding sites is not in my recent items list, so I will go to my complete parts list and find ribosomal binding sites and insert 2 of them. And now I'm going to insert this upstream of LAC-I and this one upstream of ERA C. Now if I double click on this translation rate, you will notice that the translation rate has automatically been adjusted to use the RBS strength. Similarly here, RBS2.strength. But the transcription rate is still 0, and that's because there is no promoter upstream. So I'm going to find a promoter and connect the promoter to each of the gene segments. This dotted line represents the fact that P1, promoter P1, sits upstream of RBS1 and RBS2, which means that there are 2 copies of this promoter P1 in the physical network. But since this is a schematic diagram, we can show that the P1 regulates both of these segments. Now if you look at the transcription rate, you will see that it has automatically been adjusted to P1.rate. P1.rate can be found by double clicking on the promoter P1, and it is in the function declarations. P1.rate equals P1.strength. So it's a constitutive promoter that just produces causes transcription to be just proportional to its strength parameter. Now we want lac-I to suppress this promoter. So I selected a transcription repression reaction, and then inserted that there, and then a transcriptional activation from era C to P1. Now let me press Control double click. Control double click can be used to add new control points to make it more visually appealing. And now if you double click on this promoter, you will notice that the P1 rate has automatically been adjusted to use the fact that there is a repressor and an activator. So now this lac-I is suppressing P1 and era C is activating P1. Now let's see if the system oscillates as it is. So we select ODE simulation and simulate. This was our old simulation, let's close that. And there is no oscillation. One of the things necessary for oscillation is a delay, and the one easy way of adding a delay is to understand the fact that there are intermediate steps between transcription and translation, and similarly between the mRNA and the protein production. So we are going to explicitly add intermediate steps in the translation by selecting the translation reaction arcs and using this function called add n intermediate steps, which can be found in this list of functions at the lower right or in this menu. So add n intermediate steps, and it will ask you for the number of steps you need. So let's add 8 intermediate steps. What this actually did is it added 8 intermediate steps to each of the translation arcs. So even though the translation arc is drawn using one line, it actually represents 8 steps. So I'm going to make a few adjustments to this automatically generated reaction, such as remove the mRNA and then actually use the RBS 2.strength parameter. RBS 1.strength. Now let's see if it oscillates now. ODE simulation and simulate. And you can see there is something going on. Let's simulate for a longer period of time. Well, it's approaching oscillations, but it is a damped oscillation, and that's solely because of the delay. Now if we actually increase the strength of the feedback and increase the degradation of, not the positive feedback, actually increase the strength of the negative feedback and increase the degradation rate of lac-I, you will see you get something closer to an oscillation. Now if you also increase the strength of the positive feedback, you will get a clean oscillation. Now to insert sequence information to our network, we can search the Regulon DB, search Regulon DB, and find all, for example, all the RBS binding sites, or ribosomal binding sites, and select one of them that's available in the database. And if you double click and look at the DNA sequence, you will notice that the sequence has been updated using Regulon DB. You can also find additional information, such as the Regulon DB ID and other information, such as whether it's composite or not.